what's going on? So I see this paper on Hugging Face Hub and it's got like over 500 upvotes. And I briefly read through it. I shouldn't say read, I briefly looked through it, and it spoke to this new ability to create much smaller large language models. As you can see in the title, the era of 1-bit LLMs. And when they talked about future applications, it got into using language models on mobile devices, which is something I'm currently very interested in because my favorite way to interact with a voice based assistant is on my phone. But right now, I just can't conceptualize what the most efficient way to do that in a custom way would be. So I'm really excited to read this paper and kind of just learn more about this new branch of the research. And plus, this has gotten an extreme amount of attention. So I definitely feel like I have to read it. So I'm just going to dive right in. The era of 1-bit LLMs. All large language models are in 1.58 bits. Recent research such as BitNet is paving the way for a new era of 1-bit large language models, LLMs. In this work, we introduce a 1-bit LLM variant, namely BitNet B1.58, in which every single parameter or weight of the LLM is ternary. So it's a -1, a 0, or a 1. It matches the full precision, i.e. FP16 or BF16, transformer LLM with the same model size and training tokens in terms of both perplexity and end task performance, while being significantly more cost effective in terms of latency, memory, throughput, and energy consumption. More profoundly, the 1.58-bit LLM defines a new scaling law and recipe for training new generations of LLMs that are both high performance and cost effective. Furthermore, it enables a new computation paradigm and opens the door for designing specific hardware optimized for 1-bit LLMs. And here you see this diagram, which kind of has these matrices. This is the BitNet B1.58 versus Transformer LLMs, 16-bit float. So you can already just picture why, a 1 would be significantly more efficient than a 0.2961. It's using, a single byte, a single bit. Okay, figure 1-bit LLMs provide a Pareto solution to reduce inference cost, latency, throughput, and energy of LLMs while maintaining model performance. The new computation paradigm of BitNet B1.58 calls for actions to design new hardware optimized for 1-bit LLMs. So, section 1, the era of 1-bit LLMs. In recent years, the field of AI has seen a rapid growth in the size and capabilities of large language models. These models have demonstrated remarkable performance in a wide range of natural language processing tasks, but their increasing size has posed challenges for deployment and raised concerns about their environmental and economic impact due to high energy consumption. One approach to address these challenges is to use post-training quantization to create low-bit models for inference. This technique reduces the precision of weights and activations, significantly reducing the memory and computational requirements of LLMs. The trend has been to move from 16 bits to lower bits, such as 4-bit variants. However, post-training quantization is suboptimal, even though it is widely used in industry LLMs. Recent work on 1-bit model architectures, such as BitNet, presents a promising direction for reducing the cost of LLMs while maintaining their performance. Vanilla LLMs are in 16-bit floating values, and the bulk of any LLMs is matrix multiplication. Therefore, the major computation cost comes from the floating point addition and multiplication operations. In contrast, the matrix multiplication of BitNet only involves integer addition, which saves orders of energy cost for large language models. As the fundamental limit to compute performance in many chips is power, the energy savings can also be translated into faster computation. In addition to computation, the process of transferring model parameters from DRAM to the memory of an on-chip accelerator, e.g. SRAM, can be expensive during inference. There have been attempts to enlarge SRAM to improve throughput, but this introduces significantly higher costs than DRAM. Compared to full precision models, 1-bit LLMs have a much lower memory footprint from both a capacity and bandwidth standpoint. This can significantly reduce the cost and time of loading weights from DRAM, leading to faster and more efficient inference. In this work, we introduce a significant 1-bit LLM variant called BitNet B1.58, where every parameter is ternary, taking on values of -1, 0, 1. We have added an additional value of 0 to the original 1-bit BitNet, resulting in 1.58 bits in the binary system. BitNet B1.58 retains all the benefits of the original 1-bit BitNet, including its new computation paradigm, which requires almost no multiplication operations for matrix multiplication and can be highly optimized. Additionally, it has the same energy consumption as the original 1-bit BitNet and is much more efficient in terms of memory consumption, throughput, and latency compared to FP16 LLM baselines. Furthermore, BitNet B1.58 offers two additional advantages. Firstly, its modeling capability is stronger due to its explicit support for feature filtering, made possible by the inclusion of 0 in the model weights. So again, its modeling capability is stronger due to its explicit support for feature filtering, made possible by the inclusion of 0 in the model weights, which can significantly improve the performance of 1-bit LLMs. Secondly, our experiments show that BitNet B1.58 can match full precision, i.e. FP16 baselines in terms of both perplexity and n-task performance, starting from a 3B size when using the same configuration, e.g. model size, training tokens, etc. Section 2, BitNet B1.58. BitNet B1.58 is based on the BitNet architecture, which is a transformer that replaces an n-linear with bit linear. It is trained from scratch with 1.58 bit weights and 8-bit activations. Compared to the original BitNet, it introduces some modifications that we summarize below. Quantization function. To constrain the weights to -1, 0, or +1, we adopt an abs mean quantization function. It first scales the weight matrix by its average absolute value and then round each value to the nearest integer among -1, 0, and +1. Okay, and this is the math. It says the quantization function for activations follows the same implementation in BitNet, except that we do not scale the activations before the nonlinear functions to the range 0, QB. Instead, the activations are all scaled to -QB per token to get rid of the 0-point quantization. This is more convenient and simple for both implementation and system-level optimization, while it introduces negligible effects to the performance in our experiments. So you can see BitNet B1.58 compared to Llama, size 700 million, significantly less memory, 2 gigabytes versus 0.80. Latency, less latency. PPL, I forget what PPL stands for. Is it perplexity? Possibly. And again, compare it to 1.3 bill, significantly lower memory. Compared to the 3 bill, you can get a 4 billion parameter BitNet B1.58 for 2.38 gigabytes. Right now, for example, on my computer, I can't run the 8 billion Llama. I could run the 3 billion just because of the RAM required. But, the fact that you can get it this low means you get so much more power and with significantly less latency is very exciting. Perplexity as well as the cost. Okay, got you. And then models, this is comparing it to, what is this, zero-shot accuracy of BitNet B1.58 and Llama LLM on the n tasks. So yeah, it's still competitive. Very much so. It's equal, really. Shouldn't even call it competitive. or I'll say approximately equal, slightly lower on most benchmarks. I'll say slightly though. Llama-alike components. The architecture of Llama has been the de facto backbone for open source LLMs. To embrace the open source community, our design of BitNet B1.58 adopts the Llama-alike components. Specifically, it uses RMS norm, SWI-GLU, rotary embedding, and removes all biases. In this way, BitNet B1.58 can be integrated into the popular open source software, e.g. Hugging Face, VLLM, and Llama.cpp with minimal efforts. Results. We compared BitNet B1.58 to our reproduced FP16 Llama LLM in various sizes. To ensure a fair comparison, we pre-trained the models on the Red Pajama dataset for 100 billion tokens. We evaluated the zero-shot performance on a range of language tasks, including ArcEasy, ArcChallenge, HellaSwag, Wino Grand, Pika, OpenBook QA, and BoolQ. We also reported the validation perplexity on the Wikitext2 and C4 datasets. We compared the runtime GPU memory and latency of both Llama LLM and BitNet B1.58. The results were measured using the faster transformer codebase, which is well optimized for LLM inference latency on GPU devices. The 2-bit kernel from the latter is also integrated for BitNet B1.58. We reported the time per output token, as it is the major cost for inference. Table 1 summarizes the perplexity and the cost for BitNet B1.58 and Llama LLM. It shows that BitNet B1.58 starts to match full precision Llama LLM at 3 billion model size in terms of perplexity, while being 2.71 times faster and using 3.55 times less GPU memory. In particular, BitNet B1.58 with a 3.9 billion model size is 2.4 times faster, consumes 3.32 times less memory, but performs significantly better than Llama LLM 3B. And you're seeing these here versus here. So figure 2, decoding latency left and memory consumption right of BitNet B1.58, varying the model size. And table 3, comparison of throughput between BitNet B1.58 70B and Llama LLM 70B. Look at that. Insane. Table 2 reports the detailed results of the zero-shot accuracy on the end tasks. We follow the pipeline from LM evaluation harness to perform the evaluation. The results show that the performance gap between BitNet B1.58 and Llama LLM narrows as the model size increases. More importantly, BitNet B1.58 can match the performance of the full precision baseline, starting from a 3B size. Similar to the observation of the perplexity, the end task results reveal that BitNet B1.58 3.9B outperforms Llama LLM 3B with lower memory and latency cost. This demonstrates that BitNet B1.58 is a Pareto improvement over the state-of-the-art LLM models. Memory and latency. We further scaled up the model size to 7B, 13B, and 70B and evaluated the cost. Figure 2 illustrates the trends of latency and memory. Oh, I didn't even notice that this was going all the way up to 70 billion. Wow. So where was I? Figure 2 illustrates the trends of latency and memory, showing that the speed up increases as the model size scales. In particular, BitNet B1.58 70B is 4.1 times faster than the Llama LLM baseline. This is because the time cost for NN linear grows with the model size. The memory consumption follows a similar trend, as the embedding remains full precision and its memory proportion is smaller for larger models. Both latency and memory were measured with a 2-bit kernel, so there's still room for optimization to further reduce the cost. Energy. We also estimate the arithmetic operations energy consumption of both BitNet B1.58 and Llama LLM. We focus mainly on the calculation for matrix multiplication, since it contributes the most to the cost of LLMs. Figure 3 illustrates the composition of the energy cost. The majority of BitNet B1.58 is int8 addition calculation, while Llama LLM consists of both FP16 addition and FP16 multiplication. According to the energy model in HORA 14, in that paper, I'm assuming BitNet B1.58 saves 71.4 times arithmetic operations energy consumption for matrix multiplication on 7nm chips. We further reported the end-to-end energy cost for models with 512 tokens. Our results show that as the model size scales, BitNet B1.58 becomes increasingly more efficient in terms of energy consumption compared to the FP16 Llama LLM baseline. This is due to the fact that the percentage of NN linear grows with the model size, while the cost from other components is smaller for larger models. Throughput. We compare the throughput of BitNet B1.58 and Llama LLM with 70 billion parameters on two 80 gigabyte A100 cards using pipeline parallelism so that Llama LLM 70B could be run on the devices. We increased the batch size until the GPU memory limit was reached with a sequence length of 512. Table 3 shows that BitNet B1.58 70B can support up to 11 times the batch size of Llama LLM, resulting in 8.9 times higher throughput. Figure 3, energy consumption of BitNet B1.58 compared to Llama LLM at 7nm process nodes. On the left is the components of arithmetic operations energy. On the right is the end-to-end energy cost across different model sizes. In models, stable LM 3B, BitNet B1.5 3B. Comparison of BitNet B1.58 with stable LM 3B with 2 trillion tokens. You see here it's outperforming it on every single benchmark. BitNet B1.58 is enabling a new scaling law with respect to model performance and inference cost. As a reference, we can have the following equivalence between different model sizes in 1.58-bit and 16-bit based on the results in figure 2 and 3. So 13 billion BitNet B1.58 is more efficient in terms of latency, memory usage, and energy consumption than 3 billion FP16 LLM. And that scales. So 30 billion is more efficient than 7 billion, and 70 billion is more efficient than 13 billion. Training with 2 trillion tokens. The number of training tokens is a crucial factor for LLMs. To test the scalability of BitNet B1.58 in terms of tokens, we trained a BitNet B1.58 model with 2 trillion tokens following the data recipe of stable LM 3B, which is the state-of-the-art open source 3 billion model. Both models were evaluated on a benchmark that consists of Wino Grade, Pika, SciQ, Lambda, and ArcEasy. We reported the zero-shot accuracy in Table 4. For tasks measured with accuracy and normalized accuracy, we take the average of the two. The results of stable LM3B at 2 trillion tokens are taken directly from its technical report. Our findings shows that BitNet B1.58 achieves a superior performance on all end tasks, indicating that 1.58-bit LLMs also have strong generalization capabilities. Section 4, discussion and future work. 1-bit mixture of experts, LLMs. Mixture of experts, MOE, have proven to be a cost-effective approach for LLMs. While it significantly reduces the computation flops, the high memory consumption, and inter-chip communication overhead limit its deployment and application. These challenges can be addressed by 1.58-bit LLMs. Firstly, the reduced memory footprint reduces the number of devices required to deploy a mix of expert models. Moreover, it significantly reduces the overhead of transferring activations across networks. Ultimately, there would be no overhead if the entire models could be placed on a single chip. Native support of long sequence in LLMs. In the era of LLMs, the ability to handle long sequence has become a critical demand. One major challenge for long sequence inference is the memory consumption introduced by the KV caches. BitNet B1.58 represents a significant step towards native support for long sequences as it reduces the activations from 16 bits to 8 bits, allowing the context length to be doubled given the same resources. This can be further losslessly compressed to 4 bits or even lower for 1.58-bit LLMs, which we leave as future work. LLMs on edge and mobile. The use of 1.58-bit LLMs has the potential to greatly improve the performance of language models on edge and mobile devices. These devices are often limited by their memory and computational power, which can restrict the performance and the scale of LLMs. However, the reduced memory and energy consumption of 1.58-bit LLMs allows them to be deployed on these devices, enabling a wide range of applications that were previously not possible. This can greatly enhance the capabilities of edge and mobile devices and enable new and exciting applications of LLMs. Moreover, 1.58-bit LLMs are more friendly to CPU devices, which are the main processors used in edge and mobile devices. Don't disturb me. Sorry, I don't know if you heard that, but my alarm went off. Which are the main processors used in edge and mobile devices. This means that BitNet B1.58 can be efficiently executed on these devices, further improving their performance and capabilities. New hardware for 1-bit LLMs. Recent work like Grok has demonstrated promising results and great potential for building specific hardware, e.g. LPUs, for large language models. Going one step further, we envision and call for actions to design new hardware and systems specifically optimized for 1-bit LLMs, given the new computation paradigm enabled in BitNet. So yeah, the rest is references, but these results look incredible. I'm really excited to try this out and get to work with it. I don't even know actually if it's available right now. I noticed this top comment that 25 days ago they said they'll be happy to open source the models for future resource. Stay tuned. And it currently doesn't look like it's connected to anything on Hugging Face Hub, but I need to look into this more. But really, honestly, I was just excited by this number of upvotes and by that prospect of being able to use high parameter large language models on edge devices, on mobile devices. So yeah, just wanted to come on here and read and start this practice of reading more papers live. But yeah, for now,